settling in here, has everyone made an attempt to get into the lab bright space course yet? Because I hear there's some trouble for some people. I'm on kind of a fact-finding mission to figure out. Has anybody like had trouble but not told anybody about it? No? Okay. If you find that you can't access the lab bright space course, do send me or someone an email so that we can have a full list of everybody who's affected. Trying to figure out if they like merged courses wrong or what's up with that, but I don't want you guys to get too behind, especially for a reason that's not your fault, right? Recording. Okay. So today we're going to pick up again with our arteries and really our arterioles. When we left off, we were talking about regulation. So that's still where we are today. We left off with this doozy of a slide. We're going to spend a lot of time today kind of drawing out what's going on here. So when we talk about intrinsic control or local regulation of blood flow to organs, what we're talking about is these factors happening right here at the edges of the cell. We don't need other systems of the body involved. It's all about this sort of diffusion right across those epithelial membranes. Okay. So in our normal state, we have our tissue nice and yellow. And we have our blood flow. Maybe I should have drawn that a little farther apart. So in our normal situation, sort of our steady state here we're starting, we're going to have metabolic activity going on in the cells of our tissue. Right, so they're doing cellular respiration. Metabolism is happening, they're making ATP. Which means they're using oxygen in order to break down glucose to make that ATP. So they're getting that oxygen from the blood. I'll talk about how that happens later on in this unit. But we have oxygen being sucked out of the blood, basically, into the tissue. And those cells are producing carbon dioxide as a byproduct, which then gets transported into the bloodstream to continue along eventually into our veins, back into our heart, go to our lungs, and we'll breathe out the carbon dioxide, re-oxygenate that blood. I hope I picked the same color scheme as the diagrams in your book here. I'll see you in a second. So at the steady state, you're not going to see any buildup in this region, sort of in between the tissue and the bloodstream of anything, because that oxygen is getting used as soon as it gets there. We're just sucking up all the oxygen we need, getting rid of all of our CO2. What happens when we increase the metabolism of these cells? So now we're going to do, right, like metabolism plus, something like that. Okay. So we're still using up the oxygen, right? So oxygen is still getting into our tissue. We're still making carbon dioxide, but now we're making a lot of carbon dioxide, right? So if we have any oxygen stored in, like, say, some myoglobin or something, we're using that to do more metabolism. We're producing lots of CO2, right? We may even be, doing some lactic acid fermentation. We're getting carbon dioxide from all of these processes by which we make ATP. So now we're starting to see CO2 build up here next to our tissue. So this is our CO2, right? So now we have a lot of CO2 here. So some of it is still getting into the bloodstream, but it's not getting removed as quickly just because there's so much of it building up here. So with this increased metabolic rate, we're consuming oxygen faster than we can get more oxygen, and we're producing more CO2 that can't get removed quickly enough. Okay. So we might describe this state that's happening right here on the border of the tissue and our arteriole as being low in oxygen, right? Because we're using up the oxygen, and high in CO2. Low in oxygen, high in CO2 because of this increased metabolic rate. Now, the smooth muscle surrounding the arterioles responds to those levels of oxygen and carbon dioxide. So that's the intrinsic part. Is the smooth muscle is reacting directly to these dissolved gases. What we'll find out are partial pressures, basically. Okay. So amounts of O2 and CO2 directly act on that smooth muscle. They cause vasodilation. So vasodilation, it's changing the radius of an arteriole. Is that arteriole increasing or decreasing in diameter and radius? Increasing, right? It's dilating, it's getting bigger, it's getting wider. And remember, we have this relationship between flow, pressure, and resistance, and also resistance radius, but I like coming back to this main equation. I find it's the simplest for me to remember. Okay, so as our radius is increasing, our resistance is decreasing, which means we're dividing by a smaller number, so our blood flow increases. As we increase blood flow, right now we have more blood getting to this tissue faster, which means we're bringing more oxygen to the tissue. And since we have more blood moving faster, we're also able to remove that CO2 that was starting to build up before. This sort of makes sense at this point. Does anybody have any questions thus far? I'm going to look at some pictures that aren't mine. Yeah, so that R is the resistance, but there's an inverse relationship between the radius and the resistance. So it was like the relationship between resistance, big R, and radius, little r, is also going to look like a fraction, something like that. So that is our radius. So when our radius goes up, our resistance goes down, which means our flow goes up. We could reshape this all into one big equation, but my math brain is not fully on beyond these simple equations at this point. But yeah, just pay attention to big R versus little r. That might be tripping you up. So now we see pictures. Yes, I did pick the same colors. Awesome. Okay, of what this looks like in your book. So this diagram is from your book. So we have our tissue up at the top. We have normal metabolic activity. And what they're showing you here is basically that there's kind of the same amount of oxygen and carbon dioxide because we're using the same amount of oxygen as we're releasing carbon dioxide, basically. So fundamentally, we're replacing everything we use. So you can see, like here we add 2 little molecules of oxygen come out of our bloodstream. 2 little molecules of oxygen went into the tissue, and then the reverse is kind of happening with the carbon dioxide, right? We released 2 and removed 2 in the bloodstream. So I will say in these diagrams, this is happening kind of at the capillaries, but the smooth muscle we're affecting is in the neighboring arterioles. So just don't get too tripped up about that, because we will be talking about exchange in the capillaries, but it's the arteriole that's going to be changing in flow, which is why we're focusing on that right now. still counts as local because they're all kind of right there.
What's bringing the oxygen out of the vessel?
We'll talk about it when we get to the capillaries, but it's basically the different pressures in the blood and different concentration gradients, kind of. And I'll talk about it a lot when we get to our respiratory system, as you might expect. So here we have our increased metabolic rate. And you can see we're still just delivering these too little oxygen, but now we're using a whole ton more. Right, we're using it up. We might have some in the cells already. Right. So we're depleting this area of any oxygen. Right, so we see way fewer purple dots in the center here. And we're producing more carbon dioxide than we were before, but we're still just soaking up the same amount because we haven't changed the flow, the blood vessel size, anything like that. So this is what happens that our body is then going to try to adjust in response to this increased metabolic activity. So here's where the vasodilation takes place. So that low oxygen concentration neighboring our blood vessel, neighboring our arteriole, and the high CO2 concentration is how the smooth muscle knows it should vasodilate in order to bring more blood flow to this region. And so in this image, we can see the response, right? Here we have the increased blood flow, bringing more oxygen to these cells. So now we can see they're trying to make up for it, right? They're trying to make up for the fact that the oxygen has been depleted, and they're trying to make up for the fact that carbon dioxide has been building up. And here's what that whole figure in your book looks like. But it's really just about these oxygen and CO2 concentrations. Now, we can see a similar process when we have blood flow cut off. So what we were just talking about is called active hyperemia. So active because you see it in situations like your skeletal muscle when you're going for a run, and you're doing something, you have increased metabolic demand. That's where the active is. Reactive hyperemia is a reaction to a previous reduction. So if your blood flow gets cut off because, I don't know, you are sitting on your leg weird, right? And you cut off the blood flow to your leg, something like that. So in reactive hyperemia, your body doesn't actually know specifically that you've cut off blood flow. What your body is observing at the tissue level, at the vascular level, is that same situation that we saw in the active hyperemia case, right? The only thing that's different here is why we don't have enough oxygen. So in active hyperemia, we didn't have enough oxygen because we were using a lot of oxygen. In reactive hyperemia, we don't have enough oxygen because the blood's not getting there because there's some kind of blockage. So we would draw the exact same drawing, except for the only difference we might make would be in that blood vessel coming to it, right? We might show it's like pinched off, so we have lower flow, something like that. But otherwise, everything to do with the tissue, the oxygen concentrations, the carbon dioxide concentrations is the same, right? So our problem is that we're using up a ton of oxygen and we're building up CO2, again, because we have this low flow. So blood flow is not getting to the tissue. It's also not getting away from the tissue very fast because it's all about that pressure difference. Okay. So from the vascular level, we're seeing the same low oxygen, high CO2 environment. So we have the same effect of vasodilation. The metabolites, really there we're talking about the CO2, so the byproducts of cellular respiration and cellular activity. Yeah, for our purposes, we're talking about CO2 there. So metabolites from metabolism. Yeah. So we have the same signal for vasodilation here. We do need to have a way for the blood to get there. So vasodilation on its own, if you have like a blood clot, it can't dissolve the blood clot through vasodilation. But as soon as we are able to get blood back to this area, we're going to have a really nice big blood vessel, nice big radius, nice low resistance in order to increase the blood flow and resolve this situation where we have the CO2 buildup and not enough oxygen. So we're going to remove the metabolites, which for our purposes, we need CO2, and we're going to deliver more oxygen.
Why is like this with people? Does that have to do with nerves or electrical?
I think it has to do with nerves. I'm not fully sure, I have to say. Does anybody happen to know? Has anybody ever looked that up? Never looked it up. Yeah, I think it probably has to do more with the nerves than this particular situation, based on the fact that my hand has been tingling for 2 months now after sleeping on it weird. But it could partially be due to damage from these processes, I think. I'm going to be Googling that after class. Okay. So we could trace this evolution, this process in a flow chart. Lots and lots of ways to sort of try and internalize this process. I think in your notes you have each of these steps kind of out one by one, and I recommend using those as you study to kind of predict what the next step should be. But for now, we're just going to look over it right here. So in this flowchart form, relating that to our pictures, right? We have our tissue. We're saying we've increased the metabolic rate. So we mean we're soaking up lots of oxygen, giving off lots of CO2. Right. And I drew those arrows on the same cells instead of left and right. So that's what these symbols, these upward arrows are indicating, that we've increased that oxygen consumption, we've increased the CO2 production. But if we were thinking about it in sort of like a physical picture way, we would notice the increasing O2 consumption means in that space, the oxygen concentration is decreasing. Are you with me? Cool. So that's why that little arrow is flipped as we move to our next step. CO2 production simpler. CO2 production went up, which means we have that buildup of CO2 in this region between the tissue and the blood vessel. Okay. So this is where we have the response from the arteriolar smooth muscle. So say we had an original skinny little blood vessel, we vasodilate, I'm going to rephrase it immediately. And we're going to have a nice big fat arteriole, low resistance, high blood flow. Right, so we increase vasodilation. We could add in a step here, right? If we wanted, we could say we increased radius, right? Which would mean we decrease the resistance, which means we increase the blood flow. And the whole goal of this is to correct this situation up here, right? We're trying to correct it. This is a negative feedback loop, right? The negative feedback loop, we're trying to maintain the appropriate O2 and CO2 concentration. So we're replacing that oxygen that we've used up. So we're increasing the delivery of oxygen. So now we can see that that step and our result step have the arrows paired in the same way, right? So we increase delivery, therefore increasing its concentration. For the CO2, we increased its removal. Since it's a removal, that means the concentration overall went down. So I want you to go ahead and take a second to, on the other side or in your notes somewhere, this was our active hyperemia. I want you to take a second and compare what you think would be happening for reactive hyperemia. So what might be the same, what might be different? So let's start out with what's going on in the tissue side. So these diagrams always start in green with our initial stimulus. So first thing we're going to want to do is write down why we have reactive hyperemia. What's the initial stimulus? What does it mean? Yeah, exactly. So we have loss of blood flow or anything similar, right? A blockage, loss of blood flow, not enough blood, something like that. Okay. So now we're thinking about the physiological responses to that. So what else might we put in this tissue box? We don't have to have all the same things, but we do want to say something about the O2 and the CO2.
O2 concentration going down, CO2 concentration.
And where specifically are you saying that would be happening?
We have just on the other side of the.
Yeah, exactly. So after our blockage, right? After blockage, O2 low, CO2 high. So this is really talking about that same spot, so between the tissue and the blood as this one. Okay. So we have our same situation. O2 concentration has gone down. CO2 concentration has gone up. Anybody have any other differences they want to list between their diagrams?
Could you put this diagram into two slices, like one where the blockage does get removed and one where there isn't blockage removed and then there's depth of tissue?
Yeah, you could. Yeah, that would happen if you ultimately don't replace that blood flow. The tissue would die off, underground necrosis. Yeah. I don't think your book has any gnarly pictures of that, but totally can happen. And that's kind of the problem with like heart attacks, right? That happens pretty rapidly. Okay, cool. So hopefully you didn't have any other differences here for the arterial or smooth muscle, because from the arterioles perspective, this is the same situation. So we have the same response. As soon as we can get more blood flow, we respond with vasodilation, therefore lowered resistance, increased blood flow, increasing the O2 delivery and the CO2 removal, ultimately restabilizing those O2 and CO2 concentrations. So whatever way helps you to think about these situations and sort of internalize what's going on is how I recommend you study. Try both, see what makes the most sense to you. If you want to draw for the exams, you'll definitely have scratch paper, and same deal for flowcharts. Drawing out a flowchart is totally fine too. Okay. We do have one other type of intrinsic control of the blood flow to the organ that we want to think about. Okay. So this one has to do with basically like a physical response. So we call it the myogenic response. And it's, I want to say it's almost like a reflex, right? Like with the hammer and the knee, right? So what's happening in the myogenic response is that it happens to be true that when you stretch the blood vessel out, you're stretching it because of increased blood flow, increased blood pressure moving through this. It has a tendency to want to bounce back. The smooth muscle itself responds to the stretch by constricting. So it's going to try to clamp back down. So we refer to this as a myogenic response or myogenic auto-regulation, right? So it's regulating itself, auto-regulation. So this doesn't require any external factors. So in that way, it's different than the reflex with your hammer and your knee because we had nerves involved there. But this will happen automatically. It's an intrinsic autoregulation process. Okay. So the way this happens is that we're going to respond to an increase in perfusion pressure officially. So we're going to see this term perfusion pressure in this unit and then in our next unit on the respiratory system. All that is basically is a fancy term for our pressure difference across an organ. So the perfusion pressure, perfusion is just a word describing a fluid going through your vascular system. So what we're saying here is that we have a pressure that drives blood flow, which is that delta P, which in our case, we're saying is approximately equivalent to our mean arterial pressure. That's just a new term for an old concept, if you can consider something that we learned last week old, right? Okay. So what we're saying in the myogenic autoregulation is that we have that increase in delta P, the increase in that pressure difference. And we know that our flow has this relationship to our pressure difference, which we're now calling the perfusion pressure. All right. So when we have this increase in the perfusion pressure, this is a direct relationship with flow, directly proportional. So when we increase that perfusion pressure, we increase flow. So if we're looking at an arteriole, right, this means now we have more blood, which means it's pushing out on those walls, right? So fluid's kind of always push on their containers a bit, right? Air does too, so just in general true. So we're pushing on the walls of the container. Now we have more blood flow. We're pushing a little harder. So our muscle that's surrounding, so our smooth muscle that's surrounding has some stretch receptors in it that senses this increase in pressure and responds with constriction. So we have this stretch, your smooth muscle senses it and contracts. Just how smooth muscle works. Vasoconstriction decreases blood flow. So our previous examples were largely about vasodilation, why we might increase blood flow to an area, how we might increase blood flow to an area. Right? Hyperemia, that hyper part means more. Emia is an ending that refers to blood. So we had more blood in the active and the reactive hyperemia. This is a way we can decrease the blood flow, right? So if we vasodilated a lot really quickly, too much, we might then want to vasoconstrict back to our normal arteriolar tone, our kind of baseline state. And this is a way we could have that happen. So vasoconstriction decreases the radius, which means we increase the resistance, which means we decrease the blood flow. So the overall purpose of these sort of different processes, the active and reactive hyperemia, and then this myogenic response to increased perfusion pressure, are going to allow us to keep our blood flow constant, but still be able to respond to local differences in what's going on in the tissue, how much oxygen we need, how much CO2 buildup we have. So we have a little flow chart here. So we're remembering perfusion pressure. It's really just that difference in pressure. Right, so it's like if we measured, let's see, can I draw, well, let's do a liver. I don't know if a liver is a good example. The liver looks something like that. Right, so the perfusion pressure would just be referring to, we have a pressure of the blood flow coming in. We have a pressure of the blood flow going out. And our perfusion pressure is that difference between the two, basically. So if we're thinking about it at an organ level, that's how we're conceptualizing it. But when we're talking big picture processes, we can kind of just think about our mean arterial pressure. So then this is stretching the arteriolar smooth muscle because we've increased flow, which means we're bouncing back because of this intrinsic autoregulation, this myogenic response. So questions about any of these intrinsic processes before we get to, I think next we have extrinsic coming up. Awesome. So this is kind of a throwback to some of the stuff we did yesterday, but let's talk about it a little later. But what we're looking at here is basically the result of being able to regulate blood flow at the tissue level, so to these different tissues, to these different organ systems. So here we're comparing resting versus exercise blood flow. So we can see that our original cardiac output at rest was 5 liters per minute. And we can see that our new cardiac output, when we're exercising, right, we've increased our heart rate, we've increased our stroke volume. So we increase our cardiac output, is now 25 liters per minute. So what do you think would happen if we weren't able to regulate, say, the skeletal muscle and the GI tract separately? what would the pie chart on the, oh gosh, left look like if each of these were just responding to this change in cardiac output? So remember that, so flow related to pressure difference over resistance. If we sub in our human body measurements, this is really cardiac output equivalent to our mean arterial pressure, because venous pressure is negligible, divided by our total peripheral resistance, right? So conceptually, if our cardiac output goes up, we're seeing likewise changes in that mean arterial pressure, changes in total peripheral resistance. So if everything were changing together, if this were our only sort of regulatory process, what would that pie chart look like? Exactly. Yeah, we just have larger numbers. So this is why it's important that we can regulate these things separately, that we have slightly different responses to different situations. And we'll see that this is particularly different in response to extrinsic regulation. So we're going to be talking about the effects of epinephrine and norepinephrine, therefore our sympathetic nervous system, on different types of tissue. So we can see here that because we have different processes that are regulating these different organ systems separately, our increase going to the skeletal muscle isn't really having much of an effect on these other tissues, right? So we've increased from 1 liter per minute to 20 liters per minute in the skeletal muscle. But if we look at, say, the brain, right, you're doing approximately the same amount of thinking when you're exercising, hopefully, maybe. So we don't have a big difference in terms of the sort of absolute amount of blood flow to these other organ systems. We do have a slight response, potentially responding to maybe changes in blood pressure a little bit, but these numbers are roughly equivalent. So that's because in this case, we'd be specifically doing vasodilation to the skeletal muscle, but not to these other organs. So now we're going to talk about extrinsic control. Again, we're going to come back to these equations. We've said, hopefully we know, that flow equivalent to our pressure differential divided by our resistance. Our pressure differential, right, we didn't usually write it out, but our difference, our high pressure, is our aorta. So we're saying it's mean arterial pressure. Our low pressure are the veins coming back to the heart, which we would abbreviate with our central venous pressure. But there's almost no central venous pressure. This is almost zero, which is how we get to the second equation. So cardiac output is just the blood flow from the heart. MAC is our blood pressure in the aorta. Total peripheral resistance is we added up the resistance in all our arterioles. The neat thing we can do with that equation, which we will be doing as we talk about factors affecting blood pressure, which we will come back to kind of at the end of this unit, we can reshape it, right? So that third equation we haven't seen before in this form, but it's the same thing, right? So we have this equation, that's our second equation. And we just reshape it since we're dividing by TPR over here. We could move it over here and make it multiplication. So that's how we get the TPR times CO equals mean arterial pressure. It's the same thing, we've just moved around the numbers a little bit. If we want to further put in some of the factors we've talked about, we also know that our cardiac output is equivalent to our stroke volume, so how much blood is leaving the heart any given minute or any given beat, by the number of times our heart beats per minute. So we could put that all into an equation and say that our mean arterial pressure is equivalent to our stroke volume by our heart rate, the cardiac output, times our total peripheral resistance. And the reason we're paying attention to this now is that we've talked about factors that affect stroke volume and heart rate. So when we get into our discussion of mean arterial pressure, we're going to want to keep in mind one of the ways we can adjust the blood pressure is by adjusting this activity of the heart. This resistance part, this total peripheral resistance part, we're going to see is also affected by the sympathetic nervous system and by epinephrine, which is associated with our sympathetic nervous system. A short reminder about our sympathetic nervous system. When we're talking about our sympathetic nervous system, we had different routes that we could be getting out to our effector organs. And now that we're thinking about arterioles specifically, we can specify that the effector organs we care about, right? We're thinking about smooth muscle in the arterioles. Smooth muscle and arteriole. Okay. There are other effector organs in your body, but we're focused on the vasculature here. So to get to that smooth muscle in the arteriole, we'd start with a signal coming from our central nervous system. We have a preganglionic neuron that releases acetylcholine, so we call it cholinergic. This happens regardless of which of these three routes we're taking. We'd have a nicotinic cholinergic receptor, so a receptor that responds to acetylcholine on our postganglionic neuron, but the postganglionic neuron itself is adrenergic, meaning it's releasing norepinephrine, or might be going into our adrenal gland where we have those modified cells, which we call chromaffin cells, that release some epinephrine for us. So now that we're thinking about extrinsic regulation of the arterioles, we're going to be thinking about how an arteriole responds to the nervous system, so to these neurotransmitters and to our hormone epinephrine. This is going to depend on these adrenergic receptors on our effector organ. I won't be quizzing you on this whole process and these different routes again. We covered that in ANP1, but in order to understand like why this is happening, helpful to remember that exists. We're going to be focusing on now is this receptor side. So the extrinsic mechanisms for controlling our mean arterial pressure, because we can control the radius of the arterioles and thus the total peripheral resistance, is going to be through sympathetic activity, so from that sympathetic branch of our autonomic nervous system, and from associated hormones. I'll have a number of hormones we'll talk about. Mainly, we're going to focus on the norepinephrine from the sympathetic nervous system, the epinephrine from the adrenal glands, but there will be a couple other hormones at the end that also play a role. Most of those we'll come back to in our renal section, so our section on the kidneys. So we can use these neurotransmitters and hormones to affect our arterioles. This is considered extrinsic because we saw that those initial impulses, right, were coming from the central nervous system. The central nervous system is not necessarily anywhere near the arterioles that we're affecting, right, potentially. Epinephrine, right, is a hormone we're getting there in the bloodstream. This involves systems that are not just at this tissue level, at this border between the tissue and the bloodstream. So starting with the sympathetic control. So the sympathetic innervation goes out towards the smooth muscle of the arterioles. It has a sort of general kind of widespread effect here. When we're thinking about most smooth muscle, our smooth muscle throughout most of the body has alpha adrenergic receptors. So before in ANP1, we mostly focused on the difference between alpha and beta receptors and the fact that the beta receptors increase the production of cyclic AMP. Right now, we're going to be focusing more on what the receptors are responding to. So what we're paying attention to here about alpha adrenergic receptors is that they like to bind to norepinephrine. Right? So most of our smooth muscle has alpha adrenergic receptors. Norepinephrine, when it binds to these alpha adrenergic receptors in most of our smooth muscle, is going to produce vasoconstriction. So the radius is going to decrease, increasing our resistance, so increasing our total peripheral resistance, because now that we've activated like the whole sympathetic nervous system, this is going to be kind of a generalized effect on these tissues throughout the body. And then because our cardiac output times our total peripheral resistance, this reshaped equation that we reshaped on that previous slide, since we can reshape it like this, we can see that in the sympathetic response, right, if we have our sympathetic nervous system activated, we're increasing vasoconstriction here, we're increasing our resistance. Ultimately, this will have the effect of increasing blood pressure. We happen to know that the sympathetic nervous system is having similar effects at the heart. So we actually at the same time would likely be increasing cardiac output as well. From a mathematical perspective, if we were decreasing cardiac output at the same time, we might not have this effect on that, but that's not how the sympathetic nervous system works. That's happening in most arterioles. Important to note, not the brain, but generally throughout the body. The other place than the brain that's going to have a slightly different situation is in skeletal and cardiac muscle. So we're still thinking about arterioles here. So we're thinking about blood flow to the skeletal and cardiac muscle rather than necessarily a response of the muscle cells themselves. So we're still thinking about blood flow. The difference here is that they still have alpha receptors, but they mostly have beta 2 receptors, beta 2 adrenergic receptors. These beta 2 adrenergic receptors are going to have a different response to receiving signals. Right? So it happens to be the case that beta 2 receptors, like epinephrine, so even when we're at the skeletal and cardiac muscle, those few alpha receptors that they do have in response to norepinephrine would create vasoconstriction. We can decrease blood flow to skeletal and cardiac muscle. But if we kick up the production of epinephrine, epinephrine is going to start binding to those beta 2 receptors, which has a different effect. So the epinephrine binds to beta 2 receptors. It can also bind to alpha receptors. Well, we'll practice sort of sorting these things out tomorrow, Friday, and as we go on as well. Okay. So for the epinephrine, at the beta 2 receptors, it's causing vasodilation. If it finds an alpha receptor, it's still causing vasoconstriction. Maybe let's rephrase that. If we're thinking about an alpha receptor, whatever signal it's receiving, its response is going to be vasoconstriction. But if we have tissue where we have a beta 2 receptor, we're going to have vasodilation. But it pretty much has to be epinephrine and not norepinephrine for this to have an effect. This is going to be concentration dependent. The reason for that is that if we're thinking about a cell has, let's give it like 3 beta 2 receptors. And 1 alpha receptor. If we have epinephrine, it's going to matter how much epinephrine we have when we think about which receptors are going to respond to the epinephrine. So if we have a low concentration of epinephrine, because there are all these beta 2 receptors and because they prefer epinephrine, they're going to soak up that epinephrine. And beta 2 receptors produce vasodilation. But we're going to see on Friday that if we have higher concentrations, we start to have to think about those alpha receptors as well. So as we start to have more epinephrine, some of it's also going to start getting to the alpha receptors. Okay, so we'll leave it off there and continue to think about this on Friday.